Namaste, and a very warm welcome to this deep dive.
Hello, everyone.
If you are sitting down with your books, maybe, getting ready for your next big physics test,
Or even if you're just curious about how our modern world is powered,
you are in exactly the right place.
today we are opening up Unit 6, which is all about electromagnetic induction. And this is not just theory.
No, not at all.
This is really the conceptual foundation for why we even have large-scale electricity generation.
Absolutely. Our mission today is simple. We are going to dive into the introduction of this unit, explaining the key ideas so clearly that you lose all fear of this topic.
And we'll make sure everything is crystal clear and completely safe for your exam preparation.
No confusion will remain here.
I think the importance of this unit can't be overstated, really. Until now, we've established that moving electric charges, that is, a current, always produces a magnetic field.
Right.
This unit, it completes the loop. It shows us the inverse, how mechanical energy can be converted into electrical energy, basically unifying the study of electricity and magnetism.
Okay, so let's unpack this with a counterintuitive question that, well, it puzzled scientists for decades. We knew since the early 1800s, current creates magnetic fields. Simple. But the puzzle was, could a magnet create a current?
Right. And if you ask any student, they expect the conventional scenario. You take a bar magnet, you rush it toward a coil of wire, and a current is induced.
Yes.
Experiment 6.1 proved that. Relative motion between the magnet and the coil is one way to generate this push, this electromotive force, or EMF.
Wait, can we just pause right there? Because we've used the term F a couple of times. For our listener who might be juggling terms, what exactly are we talking about when we say EMF?
Okay, so EMF, or electromotive force, it's basically the pushing force. Think of it as the energy per unit charge that an induced electric field provides to make those charges start moving.
So it's like an induced voltage.
Exactly. It's the potential difference, but it's generated without a chemical battery. It's the raw energy source that drives the current if the circuit is closed.
Perfect. Okay, so back to the magnet and the coil. Conventionally, we expect motion. But here's where the true revelation came from Faraday and Henry, and this is where it gets really crucial. What if the magnet and the coil are both held absolutely fixed and stationary?
And that's the surprise. Even if nothing is physically moving, you can still induce an EMF.
How?
Well, think of experiment 6.3. You have a primary coil connected to a battery and a secondary coil connected to a galvanometer, and they're both completely still.
Okay.
If you simply vary the current in the primary coil, like just flipping a switch on or off, you rapidly change the magnetic field it produces. This changing field then cuts across the stationary secondary coil and induces an EMF.
Gotcha. So motion is actually just one way to create the effect.
Exactly.
The true hero, the real requirement, is change. If the magnetic environment is static, steady, strong, but unchanging, the current is zero.
Yes. And this whole phenomenon is what we call electromagnetic induction. It's the phenomenon where changing the magnetic environment of a conductor over time produces an EMF. It's the mechanism that lets us create current without needing chemical batteries.
And this is so fundamental for AC power generation.
It is. It's what allows for the conversion of pure mechanical rotation into massive amounts of electrical power so efficiently.
To help visualize this, let's use a simple mental image, a metaphor we can carry through this entire deep dive.
Okay.
Imagine invisible magnetic ropes threading through a wire loop. This represents the field lines linking the area of the coil.
Yes, I like that. So only when these ropes are, interacting with the loop.
What do you mean by interacting?
I mean, they're being squeezed or stretched or cut across the loop differently with time. It's only then that they get the power to pull or tug the charges around the loop.
And that tug is the induced EMF.
That's the one.
Right. So if the ropes are just sitting there steady, nothing happens.
Nothing at all.
But the moment you start changing the quantity or the way those ropes interact with the loop, the charges feel a pull and they start to move. That's the core principle.
And if we look at the pure physics symmetry, it's just beautiful. We established that currents produce magnetic fields. Now we confirm that a changing magnetic field produces an electric field that is capable of driving the charges. The two phenomena are fundamentally linked.
So we know that change is what creates the EMF. But how do we measure exactly how much change we have? We need a quantifiable yardstick.
A way to measure it.
Yes, a measure of the total linkage between the magnetic field and the area of the coil. And that yardstick is the formal term, magnetic flux, symbolized as phi b.
And this brings us to the formal language required for your exams. The magnetic flux through a surface of area dollar placed in a uniform magnetic field B is defined as FAF BFB, Thet Aced IFE.
Okay.
This definition is critical, and you must remember it exactly as it is.
Let's break down those components because they are so crucial. Bullet dollars is the magnetic field strength, and the dollars is the magnitude of the area of the surface. But what about thanalas? And what is that bold math BFA?
Right. The bold math BFA is the area vector. It's always the line perpendicular to the surface of the coil.
Okay, so it points straight out from the face of the coil.
Exactly. And thanasa is the angle between that magnetic field vector and the area vector. This angle captures the orientation of the loop relative to the field.
And the unit.
The SI unit for magnetic flux is the Weber, WOB, or you can also say Tesla meter squared, T7222.
Let's use that rain and window analogy because I think it clarifies the three variables beautifully. So imagine flux is the total rain passing through the window. That total quantity depends on three factors, not just one.
First, the intensity of the rain, which is like our dollars, the strength of the magnetic field.
Right. And second, the size of the window, which is our dollar, the physical area of the coil.
And the third, which students often forget,
is the orientation, the tilt of the window, which is the del theta.
Yes. If you hold the window face on, perpendicular to the rain, you catch maximum rain.
And if you hold it parallel, you catch zero. So d theta is the geometry factor, and it captures the combined effects into one single measure, the magnetic flux.
And here is where we link back to the core concept of induction. Since theta BA cos theta, it means we have three distinct ways to cause the flux to change.
And therefore induce that EMF. What are those three ways specifically? This is a great conceptual checkpoint.
Okay, way number one, change the field strength. This happens if you move a magnet closer or further away.
Or change the current in a nearby coil, like in that experiment.
Exactly. Way number two, change the area, A. This is less common, but if you could somehow pull or squeeze the conducting loop, changing its size while it's in a uniform field, the flux changes.
And the third way, which is essential for things like generators.
Ah, yes. Change the orientation. Even if the field strength dollars and the area dollar are constant, simply rotating the loop changing the angle causes the flux to continuously change.
And that changing flux generates the EMF.
Which leads us directly to the law that dictates how powerful the resulting F will be. And this is Faraday's law of induction.
This is the payoff, the mathematical core. So what is Faraday's law in its exact exam-required form?
Verbatim from the source material. The magnitude of the induced EMF in a circuit is equal to the time rate of change of magnetic flux through the circuit.
MATLAB, the formula is proportional to dollar phi d.
That's right.
The negative sign is a directional issue, which we can say for Lenz's law, but the magnitude, the raw power of the induced voltage is all about that time rate of change.
Let's use that logical flow to reinforce this. Think of it in three clear steps. Step one, you have a starting value of magnetic flux linked with a coil.
Okay, a baseline.
Yeah.
Step two, you make one of the three components, ball or fade a change. This causes a total change in flux.
And step three, the critical step, you look at the speed of that change. This rate of change of flux over time, delta to delta t, directly determines and induces the magnitude of the M.
The speed matters immensely. It's like ripping off a bandage, right?
Show on.
If you slowly peel the bandage, which is a slow rate of change of flux, the pain, or the EMF, is low. But if you rip it off quickly, a high rate of change of flux, the pain, the EMF, is massive.
That is a fantastic analogy. Let's make that concrete with a minimal worked example. Suppose a single wire loop has an initial flux of $0.011 WMA. This is its linkage strength. Now let's consider two scenarios.
Okay, scenario one.
This flux slowly drops to $0.1 WMA over a period of $1 full second. The induced F magnitude would be $2.0111, which is 0.111, very small.
Very small. Okay, scenario two.
Scenario two, you rip the magnet away and the flux drops to 0.111 in a much shorter time interval, say 0.11 seconds.
100 times faster.
100 times faster. And the induced F magnitude is now Franklin 1 which equals $1.1, which equals $1. Look at that jump.
Wow. By changing the time interval by a factor of 100, we increased the induced voltage by a factor of 100. So the speed of the change is absolutely paramount.
It is everything for the magnitude of the indutensive.
Okay, time to clear up two common misunderstandings that can seriously cost you marks. Yeah. We call these the silent killers.
Please, let's internalize these corrections right now.
Misconception number one.
The field is enough trap. Students often mistakenly believe that just placing a coil in a strong, constant magnetic field is enough to generate current.
And that is fundamentally wrong. If the field is strong but steady and the coil is static, there is no induced EMF.
And no current?
Zero. You must have a change in flux. The flux has to be changing.
A good way to remember this, a hook, is no change in flux, no current in the circuit.
Simple as that.
If the flux is static, the circuit is dead, no matter how strong the magnet is.
The second trap is the angle doesn't matter trap.
Ah, yes, this is a big one.
Students, while writing formulas, they often focus only on the strength of dollars and the area dollar, and they completely forget the geometry.
That's a huge mistake. As we saw, the flux crucially depends on the orientation through that toroidal.
Right.
Simply rotating a loop in a constant uniform field still induces EMF. Why? Because theta is changing, which means the flux is changing.
So if you neglect the angle, you miss the physics of an entire AC generator.
You do.
The memory hook for this one is field, face, and tilt together decide flux. Remember all three factors when you're evaluating carry a dollar.
Let's zoom out now and connect this introduction to the larger universe of physics.
Bad idea.
We started this course learning that static charges create electric fields. Then we saw that steady currents create magnetic fields. This unit completes the picture. It shows that changing magnetic fields create electric fields that push charges. In other words, induced currents.
This circular symmetry it's really the core insight of modern physics, isn't it? And understanding this basic relationship between flux and the rate of change is your key to unlocking the entire rest of the unit.
Absolutely. This foundation opens the door to understanding how we derive motional F, the crucial logic of Lenz's law, which tells us the direction of the current.
And the full operational principles of all AC generators and transformers.
Yes. Without this basic introduction, the rest of the chapter is almost impossible to follow properly.
Okay, so for your final revision checklist, let's summarize the 4 most critical factual takeaways from this deep dive.
Let's do it. First, electromagnetic induction is the core principle linking changing magnetic flux with induced EMF and current.
Second, the magnitude of the induced EMF is directly proportional to the time rate of change of magnetic flux. The speed of the change determines the voltage.
Third, magnetic flux is the scalar quantity that measures how strongly the field links a surface, and it's mathematically defined by phi BA theta.
And fourth, this simple concept, derived from the idea of change, is the single fundamental foundation for how we generate electrical power efficiently across the entire world today.
Now that the fundamentals are crystal clear, let's just take a moment to absorb that idea of symmetry we mentioned earlier.
Okay.
We've seen that moving charges in a static field induce EMF, and static charges in a time-varying field also induce EMF.
Right. 2 different scenarios, same result.
Exactly. And this inherent symmetry, it actually hints at the fundamental role of the principle of relativity in electromagnetic induction. It's not just 2 separate events, it's one unified phenomenon viewed from different frames of reference.
That's a mind-bending thought to take with you. The simple high school physics we discussed today is rooted in the same principles that led to Einstein.
It is.
Think about how this tiny idea powers everything around you. Chalo, next time Mildhane for the deep dive on Lenz's law, where we find out which way the current flows.
Looking forward to it.
Until then, keep that curiosity sparking.